A big question that I'm certain almost no one struggles with is, what do I do when a string of decorative lights stops working? The obvious and correct answer is, buy a new string of lights. But that solution is neither difficult nor needlessly time-consuming. I want a struggle to have cheery ambiance on my fireplace mantle. Can an overcomplicated solution provide solace and fill those needs? Let's give it a try. This light set has 3 functions: a 5-hour timer, permanent on and off. After taking the cover plate off, my suspicions were confirmed. There's some sort of microcontroller involved. On a quick visual inspection, we can see a fairly straightforward circuit. An 8-pin microcontroller is the brain. The identifying label has been ground off, I guess, to try to preserve trade secrets or something. Basically, the push button pulls one of the pins low, which sets an output pin high, turning on a small NPN transistor, allowing current to flow through the string of LEDs that are connected here, consequently turning them on. The timing crystal is on the other side of the board, connected here with 2 supporting capacitors. A decoupling capacitor and 2 current-limiting resistors complete the circuit. Some initial troubleshooting with a multimeter seemed to indicate that the microcontroller pin driving the transistor was not going high when the button was pressed. This pointed towards the microcontroller itself as the culprit, but to be thorough, I thought it best to test all the components to be certain the error wasn't somewhere else. There are only 8 components on the board, so it wasn't really a big deal. The most accurate way to test these items, however, is to remove them, so that's what I did. Unfortunately, I realized after removing everything that my microscope was not recording the process. My apologies. With everything but the switch removed, I cleaned up the board with a bit of alcohol. And here's the cleaned up PCB. I tested each of the components starting with the capacitors and resistors. Everything seemed to be in order. I had some suspicion about the transistor, but it checked out just fine. Things were definitely pointing towards the microcontroller, but the last thing to check was the crystal that supplied the clock for the chip. If that isn't working, the chip will appear dead. To test the crystal, I used a function generator and an oscilloscope. The idea behind this is, if you send a sine wave through the crystal at, say, a 5-volt amplitude, and at the resonance frequency of the crystal will resonate, and the resulting amplitude visualized on the oscilloscope will increase dramatically. Now, I know a common crystal frequency for a device that looks like this is around 32 kilohertz. So I set the function generator for that frequency and started to sweep the frequency up. You can see on the scope, as I get closer to the exact frequency of the crystal, the amplitude or the size of the sine wave increases dramatically. If the crystal were bad, this wouldn't happen. Looks like this is a 32.768 kilohertz crystal, and it's just fine. With all that done, the conclusion is that the microcontroller is indeed bad. The identification of the original chip is gone, but I do know that it's an 8-pin surface mount chip with power supplied to pins 1 and 4 and ground on pin 8. With that info in mind, I looked up what I had on hand for microcontrollers that fit that description and decided to try a PIC 12F1571. With storage location in mind, I went to retrieve the new brain. The next thing to do was to replicate the circuit on a breadboard. I have my new microcontroller held in an adapter so I can fit the surface-mounted part on the breadboard. I have a push button connected to pin 6 and the base of a transistor similar to the one in the original circuit connected to pin 7 through a current limiting resistor. I also connected an LED to the transistor's collector and also used a current limiting resistor. The keen-eyed among you may notice the absence of a Chrystal oscillator. This particular microcontroller has a built-in oscillator, so there's no need for an external one. Because of that, I'm just deleting the oscillator and the 2 small capacitors from the circuit. With the hardware set up, it's time to write some code. This is not a tutorial on how to code microcontrollers, but basically, there are 3 states: off, timer, and on. Each button press cycles through these modes. In the timer section, I decided I wanted to have the lights on for 7 hours and be off for 17, adding up to 24 hours. To prove to myself that the code was working, instead of 7 and 17 hours, I set the timer to be 7 and 17 seconds. That way I could visually test the code without waiting 24 hours for the timer to cycle and complete. The circuit is in timer mode now. When the LED lights, I start the timer on my phone. When it goes out, I hit lap, then lap again when it goes on. Taking slow reflexes into account, we can see almost 7 seconds on and 17 seconds off. With that proven, I went back into the code, changed back to 7 and 17 hours, reprogrammed the chip, and let it run for a day or two. Everything seemed to work as expected. With the software tested and complete, it was time to reassemble the circuit with the brand new brain and see if this would actually work. I also managed to persuade the microscope to record this time. Started by adding some flux to the board and tinning each of the pads with a blob of solder. A quick clean with isopropyl alcohol and then more flux. The components were placed in relative position and soldered in place using a hot air station. Another quick clean, a little more flux, and the brain was installed. A final clean with alcohol and over to the bench for a quick test. First push is timer mode, second push is permanent on, third push is off. Hey, the circuit works. Finally, it was time to solder the actual LED string, connect the battery terminals, and close everything up. The trace for the negative terminal was damaged, so I made a little jumper out of some copper wire. No biggie. I put the batteries in and did a final test. Looks good. I was curious about how much draw there was on the batteries in various stages of the circuit, so I connected the lights to a bench power supply with an ammeter in series to measure the current. When in the off position, the circuit draws 212 microamperes of current. Note it's negative here because I had the polarity of the probes backwards. When switched on, it draws about 48 milliamps. That's about 8 7-hour cycles. Rechargeable batteries are a win for this device. Well, after all that, I call this job a success. Yeah, that was a lot of messing around just to get a $5 string of lights working again. But it was a fun challenge and it gave me something to think about for a while. If you liked the video or have thoughts on it, please let me know down in the comments. It's always a highlight to be able to interact with you. Time to move on to some other projects that are waiting in the wings. Until next time, I'm mainejason. Get out there and give it a try.